I'm going to go ahead and work through 2 examples with you today. I think I can get through 2. And we're going to do 2 volume problems. So I've summarized these 5 steps as draw, relate, differentiate, substitute, solve. And I'd like to practice those with you on these 2 problems. Consider an inverted cone partially filled with water. The radius of the cone is 16 millimeters and the height of the cone is 18. Okay, height is 18, radius is 16. Those 2 things don't change with respect to time. Those are fixed. Those are just constants. The things that are changing are down here in the volume that I'm interested in. And the volume is computed by the 2 properties of it, R and H. Where did R and H come from? I made them up. I made up those names. I choose the most simple symbols I possibly can, the ones that make the most intuitive sense. So R's and H's. There we go. The fact that this is 2 is that's at a moment in time. That's not all the time. It's changing, right? The volume is changing, which means that this 2 millimeters here is changing. So we're trying to ask, how fast is that changing? How fast is that 2 millimeters changing? And so approaching this problem again, what is the rate at which the height of the water is changing? Okay, that asks dH dt equals question mark. That's our objective, is to find it. And we're told that the volume of the water is increasing at a rate of 548. So I know that dV dt equals positive 548. So my mission is to relate V and H and then differentiate that expression. So that was step 1. Step 2, relate. I'm going to relate V and H. I know the volume of a cone is equal to pi over 3 times R squared times H. I've got too many variables there. I've got R. I need to eliminate. I need to eliminate R by substituting R equals R of H. So I'm going to find R as a function of H. And that's going to come from similar triangles. So observe that in my cone, it's got height 18 and it's got radius 16. And I have a smaller piece of triangle inside of there that's of height H and radius R. So using similar triangles, I know that R over 16 is equal to H over 18. And that's what I'm going to be able to use to replace R with an expression of H in my relationship right here. So then I get that H is equal to, nope, I want to solve for R. I get that R is equal to 16 over 18 times, that's an R, equals 16 over 18 times H, which is equal to 8/9 of H. And that is going to go in place of my R inside that expression. So I'll have that the volume of the water that I'm interested in is pi over 3 times 8/9 of H squared times H. And that's equal to 64 pi over 81 times 3 H cubed. So that was step 2. Step 3, we're going to differentiate, always with respect to time when doing related rates problems. So step 3, differentiate with respect to time. And look, time doesn't show up in this equation. It's implicit. So I'll get that d dt of V equals d dt of 64 pi over 81 times 3 times H cubed. And now is where all your work with implicit differentiation comes in handy. So check it out. Check it out. I've got variable mismatches, right? T is not V. They're different from each other. V depends on T, so on the left-hand side, I'll have dV dt. On the right-hand side, I get to pull out some constants. But then I've got to apply d dt to H cubed, and I'll have 3H squared times dH dt. Again, variable mismatch. T is not H, and so the derivative ends up popping up in the back there. I'm going to cancel my 3's. So then I have dv dt equals 64 pi over 81 times h squared times dh dt. That was differentiate. Finally, we'll substitute. So we're going to use the stuff that I'm given in here. And I know that on the left-hand side, I'm going to have 548 because I know dv dt is 548 because I was given it, with a plus sign to be really explicit. And then we're considering what happens when the cone is filled to a height of 2. And I don't know dh dt, but I'm finding it. And then, no, so that was step 4. That was substitute. And then finally, step 5, solve for dh dt. And so then I'll have that dh dt is equal to 548 times 81 over 256 pi. And then simplify as you will by taking out common factors from the 548 and the 256. We did it. Make sure that pi is in the bottom. That's going to be a common mistake on this problem, is to not have that pi in the bottom. So the question was, why does pi have to be in the bottom? And the answer is because if you go back to step 4, or even beforehand, see the pi is in the numerator up here. And so then when I solve for this, we're going to divide by that, and the pi is going to end up in the bottom. Essentially, I multiply by the reciprocal. That's how I think about doing this, multiplying by the reciprocal. So the 64 and the 2 squared became 256. And in my work over here, I've got my 256. My pi was on the top, and now it's on the bottom. And then I've got my 548 times the reciprocal. So that's why the pi needs to be in the bottom. One more word about this, which is that this like similar triangle relationship is pretty common, particularly if you're working with cones, whether that's an upright cone or an inverted cone. They're considering this an inverted cone. Then working with the similar triangles is really, really common for doing these kinds of things.